There is a strict, fundamental ceiling to how massive a cosmic titan can become. Even in the endless expanse of space, the laws of physics enforce a relentless boundary. For a black hole growing by consuming gas, the mathematical equations are uncompromising. Once an abyss reaches roughly 50 billion times the mass of our Sun, its growth should come to a dead stop. The mechanism behind this limit is a violent internal war. As a black hole devours matter, the blinding radiation generated by its own feeding disk exerts an immense outward pressure, eventually blowing its food supply into the void. For decades, standard astrophysics insisted that this limit could not be broken. The largest cosmic giant ever identified, a terrifying void named TON 618, weighing over 40 billion solar masses, appeared to be the absolute pinnacle of black hole growth. But 5.7 billion light-years away, deep within the southern sky, scientists discovered a shadow that shatters these calculations entirely. Sitting at the heart of one of the most chaotic galaxy clusters ever observed lies an object so ridiculously massive it defies standard cosmological logic. An abyss estimated at a mind-bending 100 billion times the mass of our Sun. That is double the theoretical ceiling. A structure so colossal it sits at the absolute outer edge of what modern physics can comfortably explain. Yet the true terror of Phoenix A star is not merely its staggering size. It is what this monster has failed to do. It is an ultimate executioner that lost control of its own domain. To understand why Phoenix A star breaks our physical intuition, you must first understand the physics of a feeding black hole. Contrary to popular belief, black holes do not act like cosmic vacuum cleaners, instantly swallowing everything in sight. In the vacuum of space, gas and dust pulled toward a gravitational singularity cannot fall straight in. Instead, the material spirals inward, forming a sprawling, flattened structure known as an accretion disk, a cosmic whirlpool swirling toward the event horizon like water circling a drain. As this gas gets squeezed closer to the abyss, it accelerates to appreciable fractions of the speed of light. At these blinding velocities, internal friction reaches catastrophic levels. The gas rubs together, superheating into a roaring plasma that reaches millions of degrees. Hot plasma shines with unimaginable intensity, blasting immense radiation and light outward into space. This sets off an endless tug-of-war. Gravity pulls incoming material inward, while the intense outward pressure of light pushes that same material back out. As the black hole eats faster, its accretion disk grows hotter, and the outward radiation pressure surges. Eventually, a critical threshold is reached where the outward pressure of light perfectly balances the inward pull of gravity. This equilibrium is known as the Eddington limit. If a black hole attempts to consume gas any faster, its radiation grows so fierce that it literally blows its food supply into deep space, starving itself. This built-in feedback loop acts as the universe's natural braking system. Furthermore, if a feeding disk grows too large, spanning light years across, its outer regions become gravitationally unstable, fragmenting into stars rather than falling into the hole. Together, these mechanisms cap a gas-fed black hole at roughly 50 billion solar masses. Yet, the cosmos possesses a major loophole. Black holes can merge. They can collide in the dark, bypassing feeding limits entirely. And deep within the Phoenix cluster, evidence suggests this exact apocalyptic scenario played out. Discovered in 2010, the Phoenix cluster is a swirling ocean of hundreds of galaxies bound together by gravity and dark matter. It is one of the most violently luminous X-ray environments ever recorded. The vast space between its galaxies is filled with a churning fog of intergalactic plasma, heated to tens of millions of degrees by the violent friction of galaxies grinding against one another. At the absolute center of this furnace stands a single anchor galaxy, and deep within its core lies Phoenix, a star. When astronomers modeled the extreme density of stars in this core, the gravitational anchor required to hold the system together yielded an unbelievable number: 100 billion solar masses. To put that in perspective, Sagittarius A star, the supermassive black hole at the heart of our Milky Way, weighs roughly 4 million suns. Ton 618, long considered the ultimate boss of the cosmos, weighs around 40 to 60 billion suns. Phoenix A star dwarfs them both, forcing astrophysicists to invent a whole new classification: stupendously large black holes, or SLABs. Numbers like 100 billion are virtually impossible for the human mind to process. To comprehend the dread of Phoenix A star, you have to map its physical footprint. Every black hole is defined by its event horizon, the spherical boundary where gravity becomes so strong that escape velocity exceeds the speed of light. For a black hole with the mass of our Sun, that boundary is a tiny sphere just 6 kilometers wide. For Phoenix A star, the event horizon spans an estimated diameter of 590 billion kilometers. If you were to place Phoenix A star at the center of our solar system, its shadow would not just swallow the Sun, Mercury, Venus, Earth, and Mars. It would instantly engulf Jupiter, Saturn, Uranus, and Neptune. It would swallow the entire Kuiper Belt and gulp down Voyager 1, which had been traveling outward at 38,000 miles per hour since 1977. The event horizon would extend all the way to the inner boundary of the Oort cloud. Our entire planetary system, along with every piece of technology humanity has ever launched, would be lost deep inside this single shadow. The geometry of this shadow is staggering. Light travels at 300,000 kilometers per second, crossing the distance from Earth to the Moon in just over a second. Yet, if a beam of light were to travel across the diameter of Phoenix A star's event horizon, it would take weeks just to reach the other side. Surprisingly, because this boundary is so vast, the curvature of space-time at the actual edge is exceptionally gentle. If you were drifting in a spacecraft toward the event horizon of Phoenix A star, you would not experience violent tidal forces or instant spaghettification. The gravitational pull at the edge of a 100 billion mass black hole is actually weaker than the gravity you feel standing on Earth. You would cross the point of no return completely intact. Before slipping into the void, your eyes would witness a bizarre distortion of reality. Just outside the event horizon sits the photon ring, a region where gravity is so intense that it forces light to orbit the black hole multiple times before escaping. Looking out into space from this zone, you would not see a clean view of the universe, but rather infinite distorted echoes of cosmic light wrapped around you in a sphere of trapped history. And then you would step across the threshold into complete darkness. The popular image of a black hole is a dense, solid sphere of packed matter. In reality, the interior of Phoenix A star is largely an empty, pitch-black cathedral. The entire mass of 100 billion suns is concentrated at a single, infinitely small point at the center, the singularity. The remaining 590 billion kilometers of its interior is pure hollow void. Falling through this shadow, you would not collide with anything. Because the distance from the event horizon to the singularity is so vast, you would fall through complete and total dark for weeks in absolute silence, waiting for a central point of impact, that takes eons of subjective descent to reach. Yet the most surprising revelation about Phoenix A star is its operational failure as a galactic regulator. Typically, a supermassive black hole at the center of a cluster acts as a thermal executioner. As matter falls in, the black hole launches relativistic jets of plasma that blast into the surrounding gas, heating it up. Because stars can only form when cold gas clouds condense and collapse under gravity, this intense superheating starves the galaxy of fuel, effectively shutting down star formation. Astronomers call this process quenching. Phoenix A star possesses active twin jets blasting out into space, carving out giant cavities tens of thousands of light years wide in the surrounding gas. But for a cluster this immense, its jets simply are not powerful enough. The executioner has failed. The thermal control mechanism is broken down, triggering a catastrophic runaway cooling flow. Superheated gas is rapidly cooling and collapsing inward. While our Milky Way lazily produces 1 or 2 new stars per year, the core of the Phoenix cluster is collapsing into an astounding 700 solar masses of brand new stars every single year. It is one of the most violent starburst events ever recorded. Phoenix A star is a cosmological anomaly, a monster so massive that its built-in feedback loops have failed, accidentally igniting a frantic furnace of star creation around itself. This leaves astrophysicists with a glaring question. How did Phoenix A star get this massive in the first place? Direct gas accretion alone could never account for 100 billion solar masses within the current age of the universe, as the Eddington limit would constantly restrict its growth. One prominent theory points to direct collapse black holes formed in the early universe. A few hundred million years after the Big Bang, the universe contained no heavy elements, only pristine colossal clouds of pure hydrogen and helium. Without heavy metals to cool and break the gas apart into smaller stars, these massive clouds stayed intact, growing heavier until they collapsed directly into massive seed black holes without going supernova. Starting with a massive head start of tens of thousands of solar masses, these primordial seeds roamed the early cosmos, merging with other giants over billions of years to construct the stupendous masses we observe today. Alternatively, Phoenix A star may be the product of a series of apocalyptic mergers between multiple supermassive giants at the core of the cluster over billions of years. As time moves forward, this violent cosmic cycle will inevitably draw to a close. Millions of years from now, the gas fuel driving this massive cooling flow will exhaust itself. The central starburst will sputter and die out. The brilliant young blue stars will burn through their fuel and explode in violent supernovae, leaving behind aging, dim red stars that will slowly fade into cold embers. Eventually, Phoenix A star will sit at the dead center of a silent, darkened web of galaxies it accidentally brought to life. It will remain as an object of incomprehensible mass, sitting in absolute darkness, outliving the very stars it spawned. For trillions of years, long after the rest of the cosmos has gone completely dark, the geometry of its shadow will endure. 590 billion kilometers of absolute silence, waiting quietly at the edge of time.